So this last section before the exam, before tomorrow's exam, we're going to talk about some applications and intervals. I'm going to actually do more than this in this section because they give it the fancy title of working with intervals. So I'm going to show you a lot of things, and it's going to be a big moral. Remember how I said, you know, we've got the fundamental theorem of calculus now, that one of the things that's good, remember that these things are all limited sums. Probably we'll see some stuff like that. Don't forget about the review session today at 3 o'clock here. And also, let me point out that when you look at the intervals on my old tests, a lot of them you probably cannot do now and will not be able to do this test. If you got a section after this, use substitution, you'll be able to do it. So there's a big chunk of those. So don't panic too much. I mean, we can go over all of them if you want. Okay, so let's look at some applications and uses. Okay, so the first thing I'm going to talk about is average value. So suppose that you went home yesterday and so you probably didn't see this on your TV. Probably not yesterday, but just sort of. Suppose you went home, the low temperature 2 degrees, and the high was 100. So pretty extreme day. What would you say the average temperature was that day? Right? So you see, everybody's seen this, right? The weather person gets on there. Oh, the high day, 100, well, it was 20. See, average 60, right? I mean, that's the most reasonable thing that you could probably do with those two numbers, right? But this would be kind of an unusual day, wouldn't it? The temperature never changed at all. Which is more reasonable to say that the average temperature of the day was 60. This one or this one? I would think probably the second. Anybody make the argument why? That's right. So this one, if you're assuming that they're monitoring the temperature all day, if I were to graph this right here, here's 60 degrees, all day long, it looks like that. Right? I mean, if it's going to be 60 all day long, there's nothing competing with 60 for the trophy of being average. 120, who knows what you get there, right? So for example, maybe your day looked like this. Here's your day. Maybe over a 24-hour period, it literally rose like that to maybe decrease heating. Or maybe your day looks like this. You didn't know this, but it was actually winter. And then, right before the 24 hours is up, the sun explodes. Right? And it gets hot. Would it really be fair to say that the average temperature here is 60? Probably not, right? Because it looks like most of the day full of freezing. And it could be the opposite, right? So here's your day, and it's 100 degrees, it's sweltering, and then comes the cold miser, and it's down to 20, right? I would think that the average temperature, some reasonable, that's the average temperature, would be really close to 20. Because maybe in the only last 30 seconds of the day. Here I would say that the average would have to be closer to 100. This one I'd probably have to agree with 60, and I would certainly agree with 60. What's the difference? How should we do the average value of a continuous function here? See, one's not quite sure what happened, right? Maybe the weather person went out at noon and saw it was 100 degrees, and at midnight it was 20. Maybe the same thing's true for this day, or maybe they were taking measurements all the time. So these are only two measurements, right? And we've seen it two measurements, and maybe that doesn't really paint the right picture of what's going on, right? This and this have both the high and low same measurements, but they different things going on with it. How can I make, if I'm taking measurements, how can I make this better? Well, these weather people are stinking lazy, right? They only go out twice a day. Maybe let's let them earn their paycheck a little bit. And instead of going out twice a day, let's send them out 5 or 6 times to take a measurement, right? And then, I mean, like if we went out, if they went out 5 times a day, they would have probably got 4 100s and a 20, right? That paints a better picture. And if they'd gone out 5 times here, they would have 4 20s and 100. That paints a better picture, right? But maybe we're still not satisfied with that, right? I mean, for example, suppose they took 5 measurements and they got 5 100s and a 20. How do you know it's not like this? What if the temperature? I think we've got a serious problem. This is what our temperature is. But over the course of the day, suppose it does this. Now, suppose that they're just so unlucky that they go out these 4 times and get a measurement of 100, and then they get a 20. How can we do better than 5 measurements? Well, we can make them go out 10 times. We can make them go out 100 times. We can make them go out 1,000 times. Measure the temperature every. We can make it go out, measure the temperature every single second. Huge spreadsheet. We get by because everybody is so interested in what every temperature every second is. On Tuesday is a huge spreadsheet with thousands of things, right? That's kind of obnoxious too, but that would certainly make it more accurate. Right? So here's the idea about how. So measure average temp over day. Take more and more measurements. So let's suppose our day lasts from A to B. So this could be 0 to 24, but I'm just going to let this point during A to B because maybe it's a day on Mercury or Mars, but these are different places. Now, what might we get our weather person to do? We might make him go out. So so for example. So I'm going to make you go out at, so I'm going to break this up into intervals, right? And I'm going to make these evenly spaced. Just to make this easy. I'm going to make you go out. I'm going to make you go out at X1 and measure X2 and measure. And every time X1, X2, X3, X4, I'll run in points at those times you're going to make them. So you're going to give me a whole bunch of stuff. We'll say that our temperature is given by the function f of x. Right? There's a function that tells us what temperature is. Right? Here the function's constant, here the function's linear, and it's also. So the temperatures are f of x1, f of x2, f of x3, f of n minus 1, f of x. Right? So I take n measurements. Right? Temperature time 1, time 2, time 3. And notice the convenient thing about n is I can let n be arbitrary long. Now, how would I get the average temperature given these readings? Well, when I said 20 and 100, what did you do? You took 2 and added them up, divided by 2, right? I had 3 readings, add them up, divided by 3. Here I have n readings. My average temperature readings are just add them up. And actually, we did this earlier when that equals 2. We had 20 and 100, and the average. But now we're taking lots. Now, keep this in mind as I sort of massage this. So we assume these are evenly spaced. You can get around that. So each delta x, each one of these widths delta x. Somebody remind me what it is? Right. Take the entire width of b minus a and divide it by however many little subintervals have, which is n. Okay, so what do we have? Our average reading is f of x1 plus f of x2 plus f of xn divided by n. But let me point out, I'm going to solve this equation up here. This gives me the n b minus a. Everybody see that? So this is f x1, f x2 F X N over D minus A over delta X. Now I hate stacking things like this, so let me rewrite this. This way. This is 1 over D minus A. So what I did is I pulled the 1 over B minus A out and I put delta X over all that. So this is what I should get if I go out and take in measurements. This is what my average should be. This is kind of a cool formula because you take whatever the length of this interval is. So for our particular example, it would be like how long the day is, 1 over B minus A, and multiply f of x1 times delta x, f of x2 times delta x, and the f of xi's, these things are all just temperature readings. Delta x is just the timing. Right, okay? Now, check this out. My average temperature. Approximately 1 over B minus A. And I want you to concentrate on the second. Anybody remember what we call that kind of sum? It's pretty much sum. And that is like sort of the stuff of life which intervals come. So let me ask you this. When I took 2 temperature readings, I got a primitive estimate what my average is. When I took 3, it's better, 4 is better, 1,000 is better. Here, I can take any number of temperature readings. How do I make this better and better? What can I do to end to make this better and better? 2 readings, sloppy. 3 readings, sloppy, better. 4 readings, a little better. 100 readings, probably. 1,000 would be more accurate. What do I do to my readings to make it more and more accurate? More and more perfect. And to make it perfect, instantly, I would want A be the limit. As n goes to infinity. Well, let me get 1 over B minus A in front. And what happens when you take a limit of Riemann sums? This should be a huge takeaway, I think, from part of the course, and it will help you a lot in the future. A limit of sums like this becomes always. So this should be 1 E minus A, interval A and B. So what are you doing? Remember the scenario where our temperature was at 20 most of the day, and then the sun blew up. How does this measure? Well, it takes the length of the day, and this is the area under the curve. what it does is, if this is your temperature function, the way you get the average is you measure the area under the curve and divide by how wide the interval is, and that gives you sort of an average height. This is kind of the way that this makes sense, right? And in fact, in general, this doesn't have to be temperature. If f of x is a, well, actually, I think it's interval, also continuous function on interval AB. We're going to talk about the mean value there, but all you really need. Then the average value of f of x on AB. So this is sort of the average y coordinate that you expect from the function is 1 over b minus a times the interval of the function. So you just measure, if that is a positive function, this is an area under a curve, you divide by the width of the interval, and then you get sort of an average height. You have something like this. This is your function. The average value of this, anybody want to guess what it is? What the average value is? What's it? This one should actually be halfway in. It's evenly sloped up, so maybe about that. Yeah, average value of the function is basically the y coordinate, where if you had a box here, it's the same area as this triangle, right? What is the area under a triangle? What this brown one is? It's half the base times the height. So if you go halfway up at the same base, and then right. Now if you have a function like this, notice this is more concentrated at the top. So the average value should probably be something like that. So the area in that red box should be the area in the front. That's because the average value times b minus a, that's just the area of the rectangle should be the same. Now there's probably the most important thing about this is the fact that this came from the limited sums. I'm going to show you some other examples how you can actually start using this stuff, doing neat things. Here's an example. Find the average value. So let me try to draw this. This is an upside down parabola. 0.10 minus 10. This is the point 0.01. What do y'all think? You think the average value is more than a half? Or so the maximum value is 1. Do I agree with that? The minimum value is 0. think maximum value is above or below? How many of you think the average value of this function should be above 1/2? How about below? Let's see. For this one, average 1 over b minus a formula. B is 1, a minus 1. Now we just got to work out the same. This is 1/2 times the interval. Now, to make this work, I need an antiderivative of this. What's your favorite antiderivative of 1? But x squared. Over 3. So this is 1/2 of, let's see, first I got to put in 1 here. Third. And then minus, put in minus 1. So this is 1/2 times, that's going to be 2/3, another 2/3. So here's 1/2. Looks like the average value is a little bit above that. Maybe right. It's like coming a way that we could have never tell that. Let me ask you this. If instead of this ground curve, if I had these triangles, red lines, what does it look like the average value is going to be there? Well, on this side of the triangle, it should be 1/2, just like that triangle. Forward, same. Right, agree. So would everybody agree that the red triangle should be 1? Well, let's check that. Let the triangle be g of x. I could write a formula for g of x. Maybe something the absolute value. I'm not going to do it. Average is the interval for formula you might say. G of x dx. Just like before. Now, I don't have a formula for G of x yet. I can simply build one, but there's an easy way to figure out what this is. I don't need to know G of x. I just need to know its interval from -1 to 1. It's like building it's the easiest way to do it. But this is my puzzle. This right here. What is the interval from -1 to 1 of G of x if it's this red function? That's right. It's the area under the curve, right? This is 2. And the height is 1. So this should be 1/2 times 2 times 1. So it comes to 1/2. So the average value of the red triangle, g of x, is 1/2. Now, can somebody explain to me why the brown one has to have an average value that's a little bit higher? You're going over the same interval, aren't you? Right? Just from here to here. The brown one is above the red, right? It's got bigger y values. So you would expect it to have a bigger average. Everybody agree with that? Okay. Any questions? Okay. Here's a big, so this is something you need to know. The average value is, of course, the way I can mnemically remember this is absolutely loosely think average value of the function, area under the curve, signed area, plus or minus, divided by the length of the interval. Here is theorem. This is called the mean value. For intervals. We already have a mean value theorem. Or good one for intervals. So what we need is we need f of x to be continuous on the interval AB. Then there is a C in the interval AB with f of C equal to the average value, which I will remind you, one of the might say. Okay, so suppose you have a function that's continuous on A. There's some point in between A and B where the value of the function is equal to the average value. Let's look at this right here. The average value of the Brown function was about 2/3. So if this is 2/3, there you go. It's about right here. In fact, I see 2 places where the value of the function is equal to the average value. For the red function, the average value was 1/2. There's 2 places here and here where but there has to be at least. And this is a good review of the ordinary mean value theorem and also the notion of the strange function from that. Okay? Define the function capital F x, the interval from A to x, t, where x can be anywhere between A and B. This is a function on the interval A B. Notice f of x is continuous on AB, and f of x, capital F of x, is differential on B. And this is about fundamental theorem of calculus. And here is why this is called mean value. What do those hypotheses tell you? All right. You got a function that's continuous on a closed interval. differential on the open interval. And so the mean value theorem applies, right? The ordinary mean value theorem that you use. F of x satisfies hypotheses of mean value on a. And so what does that mean? This means that C with F prime C this is the old mean value, right? Y'all remember this, that here is B F of B, here's A F of A. You connect this. So there's some point between A and B, say maybe C, where the slope of the tangent, that is F prime of C at that point, is parallel to the slope of the C defined at this. Now let's translate this. What is F prime of C? Well, this is little f of C. Right? Because remember, F prime of x is F of x by the fundamental theorem of calculus. That was a big theorem that if you had that function times integral, this derivative is what was inside the integral. So this sucker right here is F of C, and the single we got. This is the interval from A to B, F of T dt minus interval from A to A, F of T dt over B minus A. This interval is the interval from A to A, so it's 0. So F of C is 1 over B minus A. There you go. This is big. Mean value. Actually, I've always thought the mean value theorem for intervals is actually sort of in certain sense easier. Functions that are different. Any questions? Okay, I'm going to show you some more power of distinguishing things in terms of sums. Do a volume of a sphere, maybe something. About this. How about a company? Base radius or shifting of the arm. What do y'all foresee this? Did they teach that in geometry, or is it just kind of a curiosity? Did you ever wonder about that? About the 1/3? I mean, I pictured like a bunch of people standing around in togas with sand, dumping it in there and saying, "Oh, it looks like about a third of what you get to sell," right? I always wondered, where's that third? Is it a guess? Is it about 1/3? Is it exactly 1/3? You all have already seen this, right? You've seen these formulas. Have you ever seen them verified? No. See, this is how we count. I'm going to verify both. No. How can we get a sphere? So let's think of a sphere. This. Would everybody agree? Imagine that I'm making a little soap bubble thing here. I'll spin this around the x-axis. Then we'll make a sphere. Do I agree with it? So imagine that I've got a handle here. Crank this around the circle very fast. Sphere, right? So here's what I want to do. I want to break this interval. By the way, the sphere is R. So what's this point here? I agree with it. And here's what I want to do. And I'm going to do this a little sloppy, but because really what I want to illustrate to people is the power of remembering the limit sums is an interval. I don't know what the volume of the sphere is. That's the whole point of this problem. So what would an engineer, what would you all do? You don't know a formula, perhaps, you approximate. Do I agree with that? And here's what you could do to approximate it. Break this up into a whole bunch of tiny little intervals. Right? I'll call this one my representative here. Now, this has got some thickness to it for illustration purposes. You can imagine this being weight for weight. And that thickness is a little change in x. Everybody agree with that? Now, if you take this little sliver that I've got and spin it around, what's it going to look like? It's going to look like a bread slice out of the sphere, right? It's going to look like almost like a circle with a little bit of thickness to it, right? It's a little curvy on the top, but if that's very thin, the curviness almost doesn't matter. Do I agree with it? So imagine it's very thin. Would everybody agree that this slice that I've taken out of this spun around looks like, well, it looks like an old-fashioned vinyl LP record, right? Do I agree with that? So if I take this out and look at it, it's going to look like this, just a little tiny thickness. And that thickness is what I labeled over here, delta xi. Now, my question is this: what's the volume of this? How would you approximate volume? It's not going to be exact, but what's a good approximation? If I asked you, you all know what a vinyl record is, an LP record. If I asked you what's the volume of that, what would you do? Estimate. What does a record look like? It's a circle, right? Square record don't play too well. So it's a big circular record. So wouldn't you just compute the area of that circle and multiply by however big it is? Right? That's what we're going to do here. Let's suppose that the radius R. Let me naively say the volume of my little disk here is pi r squared times delta xi. Pi r squared is the area of the record. The delta x is how thick it is. Think of me a little volume. Now, I'm going to want to get this r in terms of x. Because the R varies, right? Everybody agree? here in the middle, my record is going to be the thickest, right? But out here, I've got a very tiny record, right? So the radius of this R, everybody hear this radius? Here to here. The radius depends on where you are, right? Very small, big, 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 small again. Would everybody agree the radius is a slack coordinate here? Right? Whatever the slack coordinate there is my approximate radius. Let me say approximate my y coordinate. Now I want that with x. Well, actually, let me do this. Actually, I don't need r, I need r squared. That makes it more. So my radius, square my radius, what I need this formula is approximately y squared. That doesn't work for me. I think this is in terms of x. I want that in terms of x. But can somebody tell me how I can write y squared in terms of x? The circle equation. So this is r squared minus x. And I really should call this x I, y I, because they're different RIs, so there can be different y's and x's. So the volume of my disk is now I. Everybody okay with that? Now that's just one record, right? I fill this up with these little records and add them up in the approximation volume, right? So what if I were to do that? Well, let's do that. Volume of this is approximately the sum of all my little volumes. Well, I didn't fix it. I don't there. Okay, so what is my little volume? Pi r squared minus x I squared. And all this says is that's one record right there. Add them all up, one to n, and that'll give you my approximate volume. I'm not exactly right. How do I make my approximation better and better? More and more skinnier and skinnier records, right? So the volume should be the limit, as even the thickest record goes to 0. Okay. This is a Riemann sum again. What does a limit of sums become? An integral. This is the integral. Pi r squared minus x squared dx. And what are my limits? Look at my picture. Where do I start making my records? When x is negative r, record, and I'm not done until x equals r. Everybody okay with me? And this is actually an easy integral to do, believe it or not. This is pi times the integral from minus r to r. By the way, anybody see a shortcut we can take? This is actually an easy function. Like, Well, that's right. We can just integrate it from 0 to r and multiply by 2, right? And that makes sense when you think about it, because actually, when we look back at the sphere, what that means is all you have to do is integrate from here to here, get the half bubble and multiply by 2. And so we can take advantage of the fact this is even. That's good practice. So this is 2 pi. Antiderivative of r squared, don't let that intimidate. R squared is a number. That's it, because x is my variable. Antiderivative of this is 1/3 x cubed. And this is evaluated from 0 to r. So I get 2 pi times r cubed minus 1/3 r cubed. And then when I plug in 0, I can see this is 2/3 r cubed 2 pi 4/3. There it is. Notice this integral goes from 0 to r. This one went from minus r to r. So when halfway and double it, you can do this. Remember, one of the things that you had this a little bit earlier, a couple of lessons ago, talking about this. If f of x is odd, and that means that when you replace x with minus x, it changes the sign of the function, then the integral from minus a to a, f of x dx, 0. And if f of x is even, and what that means is when you replace x and minus x, it doesn't change the function at all. Something like x squared plus 9x. This, the integral from minus a to a of f of x dx is twice the integral from 0 to a f of x. And this one is what we, this happens to be an even function. So instead of going minus r to r, which is more obnoxious, I went twice this from 0 to r. Yes. Right. Everywhere I see an x, I put in an r. So that's r squared times r. So there's the r cubed. And when I put an r here, r cubed. That. Okay. How about how do I we do a lot of these kind of problems in 1080, and there's usually many ways to do it. So better than checking your book, it's often good to try to work these more than you play. See if you can find. Let's see. Here's my cone. I'm gonna kind of set it in this way. And I'm gonna do the same thing that I did before. Imagine that I spin this around the x-axis. Would everybody agree when I spin this around the x-axis? This makes little records, same as when we find the sphere. This should be the point. Well, this is 0.00. What should this point be? If I'm trying to mimic that cone, it's like no. What should the x coordinate, y coordinate be? I agree. Everybody's favorite parallel. See together, H and R. So I don't think this. So, by the way, let me point out, this is y is r over hx. Because that's a line through the origin slope of r over h rising. Let's do the same thing that we did before. Let's fill this up. A whole bunch of slices. Here's my representative slice. Thickness change in x, I. And this will be the x coordinate xi here. Now, when I spin this around, again, it gives me a little record. I'm exaggerating. It's got some radius, little r, some thickness, change in x. And so the volume of my record, this here, is approximately I r squared delta xi. Now the x, notice the radius of my record changes, right? Small, and it gets continuously bigger until it maxes out here at the radius of whatever this is, r, capital. But I need this changing r in terms of x. Now notice that this is my r. And that looks like a whiteboard thing. Do I agree with that? That's that measurement right there is fine. So what is it in terms of x? So how would I get this radius in terms of variable x? It's the y coordinate that corresponds here, but the y coordinate is determined by this x. So it should be r over h. Do I agree with that? So the volume r over h xi squared 1 squared. That is the volume of just one of these discs. Fill this up with discs and add them up. This should be about let's see, I r over h xi squared. What about that? I'm taking my formula from all these discs here. Right? Added them up times however thick it was. Right? These are all the little volumes, and I added up. Because the R was straight. Yeah, because this is just by itself, this is just R. Just everybody okay? Well, how do I make this better and better? More and more skinnier boxes take a limit, and your volume should be exactly the limit as and what does the limit of Riemann sums become? An integral. This is the integral from, well, we'll get to that moment. This is pi r over h x quantity squared x. Let's look back at our picture. What's my limits there? where do I start making the record? Remember, my variable's x, so I start making my record when x equals what? 0. And when am I done? X equals. It's actually h. Right, because that's the exponent. Everybody. So let's see what we get. This is r squared and range squared x squared. Now, to avoid any confusion on my part, I'm going to pull all this junk out. Because the r and the h and the pi have got nothing to do with that, so I can pull them out. Because these up one constant. Antiderivative of x squared, 1/3 x cubed. By the way, that's where all this 1/3 is coming from. This is r squared h squared 1/3 h cubed minus 0. And 2 powers of the h cancel. I guess 1/3 h squared. By the way, a good gut check on this also is the units are right. RRH is feet, so it's in cubic feet. Any questions? All right. I have a couple more to show you kind of the power of this. Notice how I can break problems down. This is one of the powerful things about calculus, about doing intervals, is when I sum things, making an approximation, if the limiting value is something of value, right? If the limit's going somewhere that like this just passes through an interval. And as I hope you're starting to see, sometimes integrals are even easier to do than sums. Right? I'd much rather do this interval, wouldn't you, than add up a million approximations. Right? The integral's easy. Okay. Let me change this. Let's see here. Let's go. Anybody know what the square pyramid is? Well, everybody know what I'm talking about, right? I'm like a technologist here, right? Because you've got a square base and it's a pyramid, right? Somebody know the formula for this? Actually, you can see 1/3. But you might explain why I can't remember exactly the way I did it. That's right. Very good. The previous ones I got by spinning some, I put something on a spit and I spun it around, right? It's all curvy. This one that ain't gonna work, right? Because the sides are straight. So any ideas on how I'll give you a hint. We really want to do this sort of. I mean, you can't do it exactly the same way because it doesn't have that kind of symmetry. But we want to do it sort of the same way as we did the cone. Let's lay this out on an axis here. This is my x-axis. Any ideas on how we do this? what I'm going to do is here's what the cross section I'm going to do. This is my x-axis, right? And I'm going to put it over on the side illustrator here. But imagine my x-axis starts at 0 and the vertex of this thing and just pierces down to here, right? So if I drew it on the side and I only do the cross section, it'll look like this. Here's the underside of it. And this should be x equals at the end of the pyramid. H. And this should be x equals 0 here. And this length right here, what should this length right here? Just from the x-axis up. Now, imagine that you bring this up into a whole pieces again, slices. But now, when I pull this out, when I pull this slice out, what's it going to look? It's not going to look like a record anymore. What's it going to look like? It's going to be right. I'm pulling out a square, right? Small squares up here, because really the pyramid, imagine you're a kid building blocks, you're putting smaller and smaller blocks stacked up, right? These are little squares, little things. So if I pull this out and look at it, let's see if I can draw this up. It's going to look approximately like a little square with some thickness. Right here. This is delta xi. So the thickness is delta xi. Now be careful here. I'm going to call this R, Ri. Because notice my R varies. Down here it's pretty small. Up here it gets big as @1. What is the volume of my little square? Volume. Square is better. Say volume of my toast. Slice of toast. In terms of so right, so I need the surface times the thickness. So something times the thickness. What is the area of the cross section square? Right. Correct. And that's what I'm asking. What's the length and the width are the same, right? Because it's a square. What is it? What's in it? Yeah, that's right. So what should my formula be? I haven't labeled this. The length and the width should be the same thing. And what should it be? By my labeling here, which you're close. R is not enough. Well, twice R, right? Because you go down to the bottom part. So this is actually 2R. Now, I used functions before, but I'm going to do something here different, which is equivalent, but I just want to show you that, there's many ways to do it. I've got the usual problem. I want this Ri, which varies as I go here, in terms of x. Well, here's my xi here. This is out here. Now, this is equivalent to writing what the function of this line is, but there's another way to See basically some geometry we can use to get RI in terms of XI. What is this small triangle here similar to? The whole thing, right? So if I were to write this down, RI is the XI as agreed. Right? A little triangle here is similar to big triangle. So the ratio of this to this is this to this. Right? So this gives RI is R over H XI. That's the same thing. So combining this, I get 4 R H XI squared delta X. Any questions? Okay. That's just one slice of toast, right? To approximate the entire pyramid volume, I need to add up all slices of toast. See, we're like 4 R squared, H squared, XI squared, delta X. This is my approximation. Give it exact. Just take a limit. Yeah. I made a mistake with this. And I think you guys made a copy of the yellow button. Anybody know what the mistake is? It's a silly mistake. In my original picture, that's R, correct? So what should this be? Well, yeah, this should be 1/2. So all I have to do really is write oops, replace R by 1/2 R. Error in diagram. That's the good thing. So remember how I was telling you about how it's better to do things with letters and parameters than with numbers. So I made a mistake because I labeled this R by R. Agreed? And then over here, I wasn't paying much attention. This should actually be R over 2. Everybody understand my mistake? Now it's fixable. Because I'm like, okay, that should have been R over 2. So everything that I've used in my formula over here, I just replace R by R over 2, correct? If I had written 10 and 10, I'd be in much more trouble. Because now it's hard to pick out. Right? But with the mistake being in terms of R, I can easily replace R by 1/2 R. I can't replace 37 by 37 halves because it gets kind of absorbed in the formula. Any questions? So let's fix this. Picking up last. Replace R by 1/2 R. And I'll put this here. We're going max delta x I equals 0. This is going to be r squared over h squared. X squared. There we go. Because that'll become 1/4. The limit of Riemann sums becomes an integral. So a total volume should be. Well, okay. And what should my limits be? Where do I start making my toast and where do I end making the toast? X goes from where? Here, baby. So this is r squared, a squared, 1/3, x cubed, 0. This is very similar to the cone. This is r squared over a squared, 1/3. 1/3. Notice this formula is the same as a cone from the following perspective. It's 1/3 of the base area times the height. With a cone, the base area was a circle, here the base area is a square. Any questions? Okay. Let's do one more example to show you. Here's kind of a physics engineering example. And the physics example, you need to know just a little bit. Has anybody ever seen the formula of the kinetic energy? It's 1/2 mass times velocity squared. Can somebody tell me what escape velocity is? It's the speed in which you want to get out of this class today, right? So, what happens by tossing speed there? I could put a little bit more and toss them higher. In theory, I can throw this key button so hard, my big guns, that it never comes out. Okay. What speed do I have to toss this thing? How many of you have heard of a black hole? What makes a black hole a black hole? You reach the point on the event horizon where the escape velocity is the speed of light. Obviously, light can get away from Earth, so the escape velocity is something less. How do we figure that out? Yeah, well, actually, guess what? It's an integral, as a matter of fact, or that's an important piece of it, right? And actually, I'm going to let she brought up something about resistance. That's actually an important point. So here's kind of an interesting question. How many of you have heard of terminal velocity? This is what happens in the atmosphere. If somebody pushes me out of an airplane, right, and I don't have a parachute, I'm totally bummed, right? But there's a limit on the speed that I'm going to get when I hit the ground. It's going to be enough to turn me into a popular. I can catch up, but still, what happens is I accelerate due to gravity, but because of the friction in the atmosphere, I get closer and closer to kind of terminal. Never over, I don't know, 200, a couple hundred miles an hour. Right? If I die because I'm suicidal, I'll go faster. If I spread myself out because I hope to get a break, then I'll go slower. Right? So here's kind of, since you brought that up, here's kind of a question. Because of air resistance, when I throw the keys up, air is pushing down on it. When the keys start coming back down toward my hand, the air is pushing up on it. Which took longer? Trip up or trip down? Which takes longer? Trip up or trip down?
It's the same.
It's very, very close to the same, but it's not the same. Not in an atmosphere. If we were on the moon, no atmosphere, it would be exactly the same. But it's not exactly the same here. This is an interesting thought experiment, right? Which should take long. Why do you think that?
Because it kind of like changes the direction. Takes time to change direction.
Yeah. Here's kind of a thought experiment. It's hard to tell when I throw it so slow. Right? It's really hard to tell because we don't have thought. Even if I threw it up the roof, you know, we don't have equipment in here to do the experiment. But imagine that I throw it up so hard that it's faster than terminal velocity. And in fact, imagine shooting a bullet up into the sky, right? That bullet has very high muzzle velocity, right? Again, that's why it moves your body because it shoots up very fast. When it comes back down, it's limited by its terminal velocity, right? Which is fast for a bullet, but not as fast as muzzle velocity, right? So if I shoot a bullet, or if I can throw my keys so hard that they're faster than the terminal velocity, then clearly it'll take longer to come back, right? And so that should reflect on early. But here, we're assuming escape velocity, there's no atmospheric effects. We'll idealize. The first thing I got to do is I'm going to talk about work. Anybody know what physical, if you ever had like a beginning physics class in something high school, work is? I think you technically was part of the right definition. I'm going to do something like you might see in formula base. So you see two people in the gym. Which one of these is it two ideal body types can bench press more weight? Okay, what advantages does the big one have? I mean, forget the muscles or anything like that. It doesn't have to go as far. I used to work out with this guy that played baseball with. He was a first baseman. You all know what first baseman looked like? Oh, lanky, they got to be incredible. This guy had 3 joints in his arm. I mean, it was like when he was at the top of his motion, I was like, you know, like that. No way this guy was ever going to pitch a lot of weight because he had to push it a very long distance, right? You see somebody that got really big chest, short arms. When they bench press, oh my gosh, they've got 400 pounds on the bench. They're only pushing it like, 8 inches or something. That's less than somebody who pushes a lot less weight over a couple of feet, right? It's less work. And so work is basically the force resistance that you got to work against and how far you move it, right? So if you've got somebody that pushes 100 pounds, 4 feet, 100 pounds would take 4 feet. That's the same thing, the same amount of work as somebody pushing 400 pounds, 1 feet. It's kind of easy to talk about this, ideally, lifting weights in the weight room, right? But sometimes the force you're pushing against can vary, right? For example, if you're an electric field, right, there are places in the electric field where the force is very strong, and then places where it's weaker. And another place, which you might encounter this, is in gravity. You weigh more in South Carolina than you do in North Dakota. And the reason is the elevation further away from the center. You weigh even less if you're standing on the top of the mountain in Colorado or at the top of Mount Everest. Right? You're actually further away. This is not enough for you to really notice. Right? In fact, so this is kind of the interesting thing about gravity. Have you heard of spaghettification? When you go into a black hole, you know what that's about? So when you stand up, right now the center of the earth is pulling on my feet at a certain force, pulling on my head as well. My head is further from the center of the earth than my feet. So I am as we speak, I am getting stretched because the force on my feet is stronger than the force on my head. So the net force is I'm being stretched. Right? But the amount of stretch that is done to me by gravity, the difference in this is smaller than just the weight of my body. I'm actually compressing. Matter of fact, we all do it. You actually lose about a centimeter a day, and then you get back into sleep. But there is a difference in the force on my feet head. When they talk about spaghettification, if you get inside a black hole, the difference in gravity is so big that the difference between your head and your feet is large. It's like the medieval torture pack, right? It stretches you out. Yeah. You have this body of radius r, right? Mass m. And here you are on this body, you've got mass field. Because hopefully you might try to say this planet. When the amount of force you feel is G m. This is the amount of force that you feel, right? And if you've ever, you know, all these problems that we do where G is, 32 feet per second or 4.9 feet per second squared. What force do you feel yourself? Well, force is MA. The acceleration you feel, over R. This is the 32 feet per second that you feel if R is the other percent. Now, imagine that what I do is I start lifting you, right? So, now, as I lift you farther and farther, I've got to do work to lift you up away from this plane. And let's suppose that I want to lift you all the way up here to height H. This will be X equal R0. And here. So as I lift you, I'm going to bench pressing you up off this planet, right? I'm ignoring atmosphere and everything else. Now, this is a change in xi. Right? This is the amount that I lift you. And how much force does it take to lift you over this delta xi? Well, it's what, and see, this is a very small thing that I'm not going to lift you very much. How much it takes for me to lift you is how far I push you times how much you weigh, right? So force delta xi for the work over delta xi is force times distance. And the distance is delta xi. Now, how much do you weigh? Your weight is force. And your force here is G M M over x squared. Because x, this is x 0, and x is your distance here from the center of the earth to wherever it is that I'm trying to lift you. Notice my job of lifting you becomes easier the higher I push you, because you become hot, you become lighter and lighter because you're further and further away from the center of the earth, right? You're heaviest right here, but then as I get you out of space, it's kind of easier to push. Everybody okay? So, work over delta xi interval is G M M over x squared delta xi. How heavy you are, how far I gotta push you. Now, what if I want to push you all the way up to H? Well, what if I want to push you all the way here? That's how I went. Well, I add up all the works. Work done is approximately sum of G M over x squared. Everybody okay? But work exactly should be the limit . And what is sum like this become? An interval. X squared. Everybody okay? Need limits though. Where do I start pushing? And what value of x? Not 0, right? Unless I'm trying to push you out of hell, right? I start at R0, right? And H. So this is G, interval from R0 to H of x to the minus 2. That way. And the antiderivative of x to the minus 2 is x to the minus 1 over minus 1. So this is G M N times. So when I put in H, I get minus 1 over H. And when I minus, put in 1 over. So the amount of work that it takes me to push you to that height is this. Did I hear that? Okay, that's all fun formula there. But remember what we were talking about in the first place, escape velocity, right? So how would I do it? What does it mean to escape? Me to throw you up and you escape Earth? It means you never come back. Assume that this planet is the only planet in the universe, right? So I'm pushing you to infinity. What happens to this as you go? This piece goes away. Now you get G, M, E. That's the work it takes me to push you. Notice that's a finite number. So what's your escape velocity? This is the work that it takes me to push you away from Earth to infinity. But like you're going to say, and set that equal to the kinetic energy it takes. And solve this for V. So I get 2GMM over R0 is equal to M squared. M's cancel. Convenient. So your escape velocity doesn't matter how much you weigh, how much mass you have. But the escape velocity of that chair and the key need, the Empire State Building, it's all the same. Capital G is the gravitational constant of the universe. You can look that up in any physics table. M is the mass of the planet you're on. R0 is the radius of the planet or star. And so just take these numbers, plug it in, and you can find the escape velocity from Earth. The gravitational constant of the universe, that's mass of the Earth divided by the radius, it's the square root. That's how fast I can throw a baseball for it to never come back. So again, with the sums, limited sums becoming an integral, we can do some pretty powerful stuff. Any questions? Okay, well, let's do our quiz.